Let's work out the math for projectile motion, courtesy of flipping physics.
Bobby, could you please read the problem? One bullet is fired horizontally and simultaneously a second bullet is dropped from the same height. Neglecting air resistance and assuming the ground is level, which bullet hits the ground first?
Translation. We're racing one-dimensional straight down and two-dimensional. Yes, it is falling down, but it's also been launched straight across with a forward velocity. Think about it. Which bullet do you expect to hit the ground first? What do you think?
As you can see from the video, rather than using bullets, we're going to use a crossball, which will yield the same results and cost a lot less money. So we have one crossball that is dropped and simultaneously a crossball that is launched horizontally, both from the same height, which we are going to identify as H. The basic idea here is that we need to solve for the changes in time for both bullets. And in order to do that, we need to list the variables themselves in the y direction for both cases. So we can begin doing that. The expressment in the y direction for both is h. Negative h because they're both going down.
And notice that this is the same for both the one that was dropped and the one that was launched horizontally. Bobby, what else do we know? The initial velocity in the y direction is zero for both. Yes, regardless of the fact that the one that was launched horizontally has a velocity in the x direction, still, just like the one that was dropped, has an initial velocity in the y direction that is equal to 0. Billy, what else do we know? Both are in free fall in the y direction, so the acceleration in the y direction is negative 9.81 meters per second squared. Actually, I'm going to leave it as negative little g or the acceleration in gravity, because I want to point out that this is true on any planet, not just planet Earth. Now, notice that three of our uniformly accelerated motion variables are the same. Therefore, class, if three of the UAM variables are the same, what do you think is true of the other?
What do you think is true of the other?
Put it another way. Is horizontal motion going to affect the vertical motion? If you launch something forward, what will that do to gravity, free fall, and everything else that is strictly vertical? Are horizontal motion and vertical motion truly independent, or can one of them use magical oogity-boogity to affect the other?
They are the same. Yeah, the same.
They are the same. Yeah, the same.
Correct. If three of the UAM variables are the same, then so are the other two UAM variables.
UAM is what flipping physics calls uniform accelerated motion, or as we call it, kinematics and equations for first-year physics students.
More specifically, in this equation, you can see that the velocity final in the y direction will be the same. And in this UAM equation, you can see that the change in time will be the same.
And in this UAM equation, you can see that the change in time will be the same. Therefore, both will land at the exact same time.
You can see that they both hit the ground at the same time. And in fact, if we slow it down enough and go frame by frame, you can see that they actually are at the same height at the same time as well. Again, because in the y direction, all the uniformly accelerated motion variables are the same. Wait a second, right before they hit the ground, isn't the one that was launched horizontally moving faster than the one that was dropped? Actually, Billy, yes, that is correct.
It is moving faster because it's got velocity in the x direction and velocity in the y direction. More importantly, it lands a whole lot further away. In conclusion, horizontal and vertical motion, just like we saw with vector components and the law of relativity, are completely independent. One is cosine, one is sine. How much does horizontal motion affect falling? That is, vertical falling time? Not at all. They're totally independent. The only thing that horizontal motion affects, horizontal launch, affects final horizontal location, and horizontal velocity when you actually get there. Now, let's see how the math works out.
What happens when we drop an object with different masses?
We're used to seeing things falling in straight line motion as 1/2 at squared, and we can see that squared building up over time on a graph. Now, instead of looking at things just going straight down and straight up, let's take a look at projectiles, ones that go in 2 dimensions at once. Look at that gorgeous parabola that you see as things get tossed through the air at different speeds. We want to graph those positions over time, and what's more, we want to graph the actual trajectory, the path those are making in space, a real-time photo in addition to the graphs of 1/2 AT squared. We've got a horizontal component of motion. If this is our initial velocity, we can say that this is our initial horizontal velocity. Gone are the days when we simply write VI with a vector sign. Now we have to specify, always, always, always. This is the horizontal component, and this is the vertical component. Let's take the horizontal component first. Horizontal motion is very straightforward. Gravity doesn't work in the horizontal direction. What difference does it make that you're moving vertically? Absolutely nothing. So after 1 second, we're still going the same VIX. After 2 seconds, we're still going the same VIX. After 3 seconds, we're still going the same VIX. Horizontal motion is completely consistent. That means those horizontal equations are going to be just lovely. Our initial horizontal velocity, as you can see, is simply the adjacent component of the velocity. That's VI cosine theta. Now, under normal circumstances of accelerated motion, our final position in the horizontal takes our initial position, adds our initial velocity building up over time, plus 1/2 AT squared, which A in the horizontal direction this time. This is the standard horizontal equation for two-dimensional motion. Record it, be clear on it. If you've ever got drag chutes or rocket boosters or wings, you are going to need this equation. But if you are a projectile, and projectile by definition is free fall in 2 dimensions, free fall is vertical. Gravity does not work in the horizontal direction. And this simplifies into the lovely, lovely equation that your change in displacement is equal to your initial velocity times time. That's VI cosine theta times your time interval. Done and done. That's all that's going on in the horizontal direction for a projectile. It's consistent. It never changes. Now, the vertical direction, that's where things get more interesting. Even if you're a projectile in free fall with no rocket boosters and no air drag. Starting with an initial velocity, you see here it's just up and down. That would be opposite. That would be VI sine theta. You'll notice that already that velocity is going to change. It's going to slow down as you get higher and higher up until finally, after all that slowing down, you're not going to have any vertical velocity at all. And then you're going to start picking up speed on the way down until you finally land. You will need an equation for your final velocity. Final velocity in the y direction. VF, last we knew, was VI, leave the space, you'll need it, plus acceleration times time, right? VI plus AT. Well, the t is going to change, but our initial velocity is our initial velocity in the y direction. That's VI sine theta. And our acceleration is negative 9.81 meters per second squared. Please note, g is positive. I'm going to say that again. G is the strength of the gravitational field, as in MGH. MGH was never negative. G is not negative now. 9.81 meters per second, straight down. That gives you your final velocity in the y direction. Similarly, the final height we've fallen, YF minus YI, is going to be VIYT plus 1/2 AYT squared. Let's see. Initial velocity in the y direction is VI sine theta, multiplied by that by time. However, our 1/2 AT squared here does not cancel out. We still have 1/2 of negative 9.81 meters per second squared times t squared. If you also want to know that delta y equals byf, whatsoever it may be, t, plus 1/2 gt squared, note the sign change from byi to vif, that equation will still work, as will vy leave space squared equals vi squared plus 2a delta, well, it used to be delta d, now it's delta y, and in the y direction acceleration is negative 9.81, but all these have to be tagged with a letter y. This has to be initial vertical velocity. This has to be final vertical velocity. All these guys are all tagged with y's. It's all in the vertical. Please note that the letters x and y never appear in the same equation. Vertical motion and horizontal motion are completely independent. Tidy up your 8 equations and box them. You are good to go for the next 2 years of projectile motion.